central difference. Different simple for this operator, central difference operator, we can call it. Let's call number 5. I am in different literature there is a different symbol, because the point is if you have to define operator, you can define it with this definition and you can use any symbol. So different symbols exist, but for central difference operator, usually the symbol that we use is represented as delta, sigma, sorry, small delta or sigma, I don't remember. We call it sigma, small sigma. And I remember, if I roughly, delta is something like that. So this is yes, so this is a small sigma. So what does central difference do? If I apply to any function f of x, it is quite clear from its definition as well, but before to give its what we call it, like it's a definition exactly, because we can define it in a different ways as well. So let's have some representation, graphical representation first, and then we will try to figure out what does this mean. So if there is an x-axis of any function and there is a y-axis for any function, and there is an x, there is a y-axis. So I plot that function to a certain extent. Okay, so if I am interested on this height, let's say this height is belongs to some point x here, which is belongs to domain obviously, and this is the function y equal to f of x, and obviously we know the any point that is ahead of it in a forward direction is h, and any point which is at the back of that point in a backward direction is x minus h. So we know forward, backward. My objective is still what the central difference do is try to compute the difference based on the central values. What this means here, very simple idea. So I want to compute this operator on this point, at that point. Okay. So, but I already used the word. It could be defined in a different ways as well. I am using here the full length. That is that a point which is situated at a distance of h forward and a distance of backward h unit. So what does central difference do? If I ask you what is the value here, so let me point out. So what is the value here? So your answer is f of x plus h. And if I ask you what is the value over this height of point x minus h, your answer would be f of x minus h, because these points are selected by us and we know this function, so we can plug each point in it to get this value. So it is very simple in this case. Okay, so what central difference do? It is not a differential in this case, it's just a difference. What is central difference do is try to compute the difference. You have to apply it at certain value. So I want to compute difference on this value here. So what it looks towards this right hand value, and then it also looks towards this left hand value, that is a backward, and based on that it will try to analyze which difference is better in this case. So what we do in central difference, we compute it like that: f of x plus h minus f of x minus h. So this is simple central difference. But question is, why it is called central? Because if you look with reference to this point x, this value x is exactly midpoint of these 2 points, because this point is situated, for example, h is 0.1. So this point is situated exactly 0.1 distance of this unit, and similarly it is h. So this is also the h distance, and this is also the h distance. So if you compute the midpoint of these two, you will get exactly the central value x in this case. So this means that I want to compute a difference or a change belongs to this point based on the central values, the values which is lie at the center of these 2 points. So how do we compute? This is the definition. This value, forward value, subtracted from its backward value and divided by central difference. This is simply a central difference. So very simple. You just need to compute forward subtracted from its backward value. So if you remember correctly, in the last lecture, I tried to connect one difference operator with the other operator as well. So here, if I look carefully, I can do one thing as well. What is that? I should okay. So I am right. This is the definition of the central difference. This is the only thing you have to memorize. But we can write down it in a different way. I'm doing it directly. You have to let me know you understand it or not in a lab session. What if I directly write down this quantity e of f of x? Do you remember this quantity? This quantity, it is a shift quantity if applied to x. Similarly, subtract, this could be written as e minus 1 of f of x. If you remember this quantity, I said this is also a shift if applied to f of x, but in a backward direction, 1 unit. H is a 1 unit. So we can say central difference, which is numerically defined like that, is in the terms of shift operator will be defined like that. So what is the relation we can observe from it? If I remove f of x from both sides, if I remove f of x from there and there as well, so what will I will get? I will get the following relation. So the relation between central difference and shift operator E. So what would be the relation now? So relation is quite easy. Central difference operator is equal to shift operator minus backward shift operator. So this is the relation. Or if we try to simplify a little bit, which I didn't explain, you can do the following calculation as well. If you like, 1 over e could be written as well. 1 over e means it is a shift operator but applied in a backward direction. So if you multiply this quantity, you will get e square, that is shifted twice. I told you, you can shift half of the length, twice of the length, thrice of the length, minus 1, and we don't usually write 1, we can write operator, identity operator. You remember I told you it is similar to 1. If you multiply it any function by 1, you will get the function here. So if you multiply with the operator identity, you will get the function again. So both are same. Instead of 1 in operators, we can sometimes use I as well, a shift operator, because it does not make sense to have an operator and a numbers in a one equation. And e, so this is the one relation that you can have. Obviously we can express this relation in other forms as well. In books you can find different ways. Sometimes this is multiplied here, and instead of identity you can bring some other values of the forward or backward difference operator, and other things are also possible. But this is just a redundancy, that when you need, you can express one operator in the terms of the other. But this is the just for your idea, the central can be linked with the shift operator by this the representation. Okay, so this is one more operator for you, is called central difference operator. One thing, student, I want to point out, which I already said in earlier, but then I didn't focus much because I thought that it will create some problem for you at that time. So this is the definition you have to know, and this is the relation that it has with the shift operators. Okay, you can obtain some relation with the forward or backward central difference operator, which maybe I will put in a quiz or some other exercises that you have to figure out yourself. It is hardly 2-3 lines exercise. It's not that difficult. Okay, so I said in earlier, I have some space, so I will use this space to express what I want to say. So I said earlier that central difference could be defined in other ways as well. For example, I can define a central way in this form. This is it will make little bit confusion, but concept is the most important thing. Representation is not important. The point is, let's say this is the function, and similarly there is some value x, and we know that at a distance h there exists another value plus h, that is a forward, and similarly there exists some value x minus h. So what I did, let me change the color of the pen so that you can see it easily. So what I did, so you all remember, if I move from there I will end up there by covering a distance of h amount. Let me write down again h amount. Okay, so question is it necessary to go for a complete 1h? Can we go some other length as well? Then answer is yes, we can do it like that. If this is the point, then this point which I am representing as a cross, assume to be it is the midpoint of these 2 points, which two, x and x plus h. So the coordinate of this point is based on this x could be clearly written as x plus h by 2. I hope you understand. The coordinate of this point is could be written based on x is x. If this length is h and this point at the midpoint, so I can say x plus h by 2. Whatever be the length, half of this length will be added to this, you will reach to that point. Similarly, if you want to go to this point backward direction, you do not need to subtract complete h, because if you do that you will end up here. So what you have to do, you have to subtract half minus half of h by 2. So you have to move to this direction. So the coordinate of this point is quite clearly understand that this is equal to h by 2. The cross, since this cross is not mixed with the, let's make it steric. This is not x, they are the point. So these the red points, if I want to compute, they are, this point is still at the central value of this point, because they are half our distance ahead, half our distance back. Both have a length of the interval is still h. Keep in mind this point. So in this case, if I want to define a central difference, so I can do it. So I can do it like that. What I will do, I will select this point, I will select these 2 points, and I will compute this quantity f of x plus h by 2 and f of x minus h by 2. I think maybe someone of you cannot see the red color. Let's use blue one. So if you have any problem, it's not that difficult one. So I'm using blue color now. So it is the same thing but with the blue color. So I compute f of x minus h by 2 and f of x. So if I want to define a central difference of this quantity, I can do the same thing, because for central you just need to look what are the values that are situated at equidistance such that this value becomes the center of those values. So I can clearly compute still f of x plus h by 2 minus f of x h minus by 2, so that I will get the central difference operator. So basically this represent the height of the difference of these two quantities, this difference based on this value, not this value. So if I define central for this diagram, so I can say central value of f of x is equal to f of, I think I do not have enough, f of x h plus by 2, and I'm writing down what, minus f of x plus h, sorry, minus, this thing would be minus, so this will be f of x minus h by 2. So this is also a central difference. So if you found in a book a different representation, do not confuse, because central differences means you have a central value and you want to compute a change based on the values that are situated in a both direction equidistance, that is forward half, backward half in last example, or a full length forward, or you can do it other way as well. For example, a point which is situated 2 units away from both sides, you can apply the central difference strategy there as well. So there is number of ways to compute the central difference point. I hope this operator point is clear to you. So let's move ahead, and we will try to explain some more concepts related to that. In fact, the point that I highlighted earlier, we have to discuss that topic, but this is some idea. Okay, so I hope it is clear to you. If I use central difference, so you are basically saying I am computing a change based on the points that are lying on the left and right hand side of that point. Simple. So it could be defined in different ways. Okay, students. One thing I want to highlight before moving to the next slide. This relation is based on these definition, which is the basic definition, full length definition of H. If you can similarly express a same relation based on this expression as well. How? I have some space, so before moving to the next slide, I can write down that del f of x is equal to f x plus h by 2, means you have to shift the value half of the distance forward direction plus h by 2. So so in this case this means that we have to move forward. So what I will do, I will put plus half, okay, of f of x. So if you have to value other than 1, you have to write down plus half minus e, we have to shift negative half, that is half of the backward direction of f of x. So this is the point. So one can clearly see if I remove f of x from both the side, I will not get this type of equation. I get something del equal to e raised to the power half minus this minus e raised to the power minus half, where minus half means you have to move backward half of the length if it's not a power, and similarly for that. So these are the similar relations. So you can define it in many ways. Operators are too many things to move from one point to another, but the main concept you have to understand, whenever you are dealing with the operators central, you means you want to compute the change on the values that lying on the neighborhood of that point at equidistance. That's the main point, so that that value become the center of the data set. I hope these 5 operators are enough. There exist many operators, but we think these operators are significant for our purpose, because we need to discuss a finite difference method. We need these type of operators and other things. Okay, so let's move to one point which is important, which I started earlier in the last slide, but I remove it. The question is, how do we define higher order derivatives? Or obviously it means a higher order derivative based on operators. Based on operators. So it's just a question. It is not a topic. It's just a question, which is basically deduction or extension of this topic. That we just learned that in today's lecture, the differential operator is defined like this for forward sense or backward sense. Now question is, we learned at the calculus level, first year or second year or maybe inter level, that we can define derivative as a second order as well, or third order, or fourth order, or fifth order. Here the derivative that we have defined is only a first order. First order. Here it also sense is different. It is forward based, it is backward based, but both are first order derivatives. Dy over dx. Nothing is more than that. What if I have a second order derivative? So can I use it? No, obviously this relation, these two cannot be used. Although they are first order defined, but we cannot use it. We have to modify them. How? This will be answered in this slide. So let's focus on one part. Let's focus on the forward operator first, and then based on that we can define all other operators. So you can extend it very easily. So let's recall the definition. We have this operator first order d f of x approximately equal to, if you compute forward of our function f of x divided by some amount h. Okay, some finite amount h. It should not be 0. Okay, so this will give the approximate result of first order derivative. So this is basically called first order forward differential forward difference, sorry, forward first order but forward difference. Okay, in order is related to the derivative term. First order forward difference of sometimes we call it forward differentials, and similarly you can define for backward, but I am focusing on the forward operator. Okay, so question is, what does second order, because one thing just to connect, this thing is defined as d f of x upon dx. So these two are equal because they are saying derivatives of the functions, but numerically when you compute you get approximations. So now what we want to compute, what we want to know, what would be the value approximately based on forward analysis of this quantity f of x. What would be the value of this quantity? The same concept is quite simple and very easy. You can easily grab this idea because usually I'm not going to show for third order or fifth order. You understand one time and you can do it for whichever order you want. You need to work out little bit, but in books you can find the relations directly. So mostly you have to memorize the point. Okay, so how do we compute? First the question is it we use the same symbol d to represent second order derivative? That's the first question. Or is there any other way? So the answer is we cannot use same symbol because I already told you this represent the first order derivative. So we cannot say d equal to this quantity as well, then it will cause a confusion. So what we do in this case, or what we should do in this case, is we have to figure out some relation. So let's say I said or yeah, I can define it. So let's say it the symbol that we use, then I will explain why we use, we call it d2 f of x. It's very simple. What does it say? It says d2 is a power of f of x. Think about it, what I'm trying to explain just now. Okay, so what does this says is, if you remember, if your teacher asks you compute second order derivative, so what you do in practice, in reality, so you remember that you said, okay, if we have to compute first second order or third order, so we cannot do it directly. We have to first compute first order and then we have to differentiate that function again so that we can get second order. And if we want to compute third order, we have to differentiate the second order derivative again so that we will get third order, and so on. So this means that if you want to compute higher order, that is a derivative greater than 1, you have to do it in a stepwise, one by one. So what does this means in operators? So whenever we say operators, we have discussed a little bit closer to that thing as well in our last lecture, but let's focus here. So what I just said, you apply first derivative and then compute other derivative. What does this means in operator? So in operators is similarly exactly the same what I just said. What you have to do, you have to apply operator twice. So what you have to do, you have to first apply operator d of f of x on this function, and whatever be the answer you get in this bracket, you have to apply d again. Now the question is, what is the derivative? Because we just learned that the first order derivative df of x is defined like that. So what we have to do, we have to compute first order derivative. So this part will be replaced here, and then we have to apply this definition again on this function. So in this way we will get the second order derivative. So that seems okay. So we understand that this quantity is defined like that, first order, and then we have to apply a second order differential term on this operator. Keep in mind that it is only d, it is not d, so you cannot multiply this part by this part or saying that we have a second order derivative. No, it's not like that. We have to think. So let's think about it, how we can do this thing here. What would be the strategy we should use? So so to apply this derivative, you need to understand some concept. So number one, the first point that you have to understand, I'm not making a drawing there because for me the axis is most important for operator. So if this is the point x, then this is the point, let's call it x plus h. Then the point which is situated ahead of it can be labeled as x plus 2h. Okay, and so on. I hope you understand what this means. And similarly, if this is the point, reference point is x, then the point which is one step backward is called x minus h. Similarly, the point which is uh, two step backward is called, can be represented x minus 2h, and so on. I'm not plotting. Obviously, there is some y-axis, so you can understand that there must be some graph going on, but it is not necessary for our. So now what we have to do, student, we have to think like that. So if I ask you that I want to compute the change, let's draw it. In fact, it is much easier for you. So the part and go. Okay, so there is some function f of x, and you want to compute its second order derivative. So what does this equation is saying? You need to know the first order derivative first, and then you have to apply the differential operator again, so that you will get the again the difference operator there. So how we will do that? What is the strategy that we will use here? So student, it is quite simpler and very easy for us. D f of x, in our case, we know that this quantity, it may be a little bit complicated for you, but let's think about it. D f of x. D f of x, this quantity in the bracket is basically df of x. So df of x in our case, in a forward sense, is equal to this. Why I said forward sense? Because same thing can be done in a backward operator as well, but we are focusing on the forward. So forward differences. So this quantity could be replaced in this bracket. So if I do so, just to save a time, I am doing it like that. I hope you understand what I did. F of x plus h minus f of x. This is all divided by h. Understand what I did? I replaced this whole quantity in a bracket, and I also opened the forward difference relation. So I did this like that. Okay. Okay. So so okay. So this is the basically what we have to do. So now this is the second order derivative, and second order is represented by d2 f of x, d2 f of x. Now, question, one thing you can clearly see, this amount, that's h, is a number, is a numerical value. Let's say we said we have a data at a distance of 0.1 units from each other. So this is a 0.1. It's a known quantity, it's a number which is not changing for a given data set. This remains the fixed. So it is a small quantity, but it is constant to that extent within the data. So what I am doing, I'm taking it out as operator, because operator cannot be applied on this quantity, and then this differential operator will be shifted to this value, this function, and this function separately. So this is the important point that you have to keep in mind. I can only shift this operator, derivative operator, to this function and this function, because this differential operator is linear. If it is not linear, I cannot do this. So here these two functions are similar. It is just like you do many times. You remember, if there are two functions that are adding, for example, I can use this rough space. For example, ex plus sin x. if I ask you, so find the first order derivative, because this dy over dx is just like this d, and let's assume this h is taken outside, it is somewhere there, 1 over h, and this function is something represented ex and this function represented ex, although in this case the function is same, but let's say they are two. So if I ask you how to compute derivative, this whole part is a rough work. So what you do in this case, you know that you have to shift this operator here, and you can compute the derivative. It is because the linearity, the differential operator is linear in nature, or every operator does not exhibit this quantity. What does this showing is showing that what does this tell us? It says that if you add two functions and compute derivative is same as if you compute derivative individually and add them. So we have to do the same thing here. There are two different points at which we want to compute the change now. One is f of x plus h, f of x, but first order. So what I do, I have to shift this and then compute the change. So what I will do, I will apply this d operator on this function and d on this function, and then compute the change individually, and this 1 over h will be taken out like 1 over h. So I will continue in the next slide from this part. Maybe I will just for the connection. So what I'm doing next slide, I'm just shifting this d with this one and then this one along with this one and taking 1 over h as a common. So what will we get here? So d2 f of x, that is second order derivative, approximately define as sorry, here it is not approximately, is equal to 1 over h taken out common. Yeah, we can say approximately as well because we already opened the forward difference, so this is not a problem. It is defined as d, I'm using bracket, f of x plus h minus what, f of df of x. So it is shifted, that d, let me go one time more back, this d is shifted to both of the values at different points. Okay, so h is taken out as a common. So now what we have to do, we have to figure out what does this means. So let me write down one thing again. For this is not a problem for you, I hope. For this there will be a no problem because you all remember. In fact, let me write down again. You all remember? You remember that d f of x. If you remember this relation, you can figure out all the relations. That is equal to what? Forward sense df of x divided by h. So I can clearly do one thing. This part df of x is exactly replaced by this quantity. Again, I made a mistake, is approximate. So this quantity will be replaced in this portion, and here I have to think. So if you look carefully, you know the answer already because you have to build a symmetry. What you have to say, you have to think, if f of x is there, so what is the difference here? It is also a first order operator, but the difference is here we have f of x and here we have f of x plus h. You see that? This is simple, f of x, and here just f of x plus h, but both are operating with the same operator, derivative t operator. So if there is f of x and we want to apply differential operator, we have this relation del f of x upon h, forward sense. So I will replace this part directly here, no problem. But what should we do to this term? So we have a very good symmetry. I just explained. If there is f of x, so there comes a del f of x. So it is quite clear. If there is d f of x plus h, this means that here should be del f of x plus h. Let me write down separately first before going to the equation. So what I'm saying, if this is the relation, then f of x plus h must be approximately equal to forward of f of x plus h upon h. Why? So I just gave you an example where I compute a derivative at point A. The point A could be any value. So point A could be a plus h as well. So however, definition remains the same. Definition says any point x, if you want to compute first order derivative, could be defined in forward sense like that. So this is also one of the point in the domain x plus h, and I want to compute a derivative first order. So this could be defined like this one. It's very simple. So if I replace these two quantities, so what I will do now, I will replace this part with this quantity, and this quantity will be replaced by this part. So what will we get? What will we get here? We get del f of x plus h. So keep in mind, forward difference operator is just an operator. Definition remains the same. It does not matter at which point you apply it. Minus del f of x. If someone is thinking why I am shifting to this mode, the reason is this is just a symbolic representation. What you are trying to say, I want to compute first order derivative at this point, and I want to compute first order derivative at this point, and I want to compute the difference of these derivatives. If you cannot know how we can compute that, for that you have to always go back to this relation. So this is because you know the function and you know the points. Okay, so story will not end here. So one thing, there is no operator left apart from the forward difference. So what I can do, I can take out h again common. So what we left here, let me excuse it a little bit so that I can finish it in this slide. So this will become 1 over h. This is already there, and there are two more. So if you take the LCM, you will get this 1 over h here, and then this h. So you will get 1 over h square. And the other thing is left is forward of x plus h point minus forward difference of f of x. So since this in books you can find this is also the definition of the second order derivative sometimes, but I want to simplify it further so that we will only get one simple equation that we memorize all the time to have a second order derivative for the forward differences. But to know that to complete that part, I have to go back to one slide because I draw something there which I did not highlight it much. You remember this part? So in this slide, if you remember, if I ask you which one is the right hand side point of x, so you can say x plus h, x plus 2h. But if I say exactly which one is the closest to the right hand side, the answer is x plus h. Similarly, which one is the left hand side? The backward is x minus h. Also, x minus 2h is also at the backward. But if I ask you which at this point, if I am at this point, not at x, at this point, which one is forward point? So your answer is x plus 2h. Similarly, if I ask you if I am here and which one is his backward point, so your answer is x minus 2h. So this means that if I compute f of x is this value is f of x plus h, and this value is f of x plus 2h. Okay, so if I ask you to apply a forward difference, so you know that you have to subtract forward value to this value because you are applying forward to this point. So the forward value is this quantity. But if I ask you to apply the forward at this point, so you have to subtract it from the forward value that it has, and the forward value it has is x plus 2h, f of x plus 2h. If I ask you to apply a forward difference, so you know that you have to subtract forward value to this value because you are applying forward to this point. So the forward value is this quantity. But if I ask you to apply the forward at this point, so you have to subtract it from the forward value that it has, and the forward value it has is x plus 2h, f of x plus 2h. So definition is still the same. You have to look for the just immediate forward value, but you have to subtract it as well. In order to subtract, you have to look carefully. So let me use this information on the next slide. So if I want to compute the forward difference at this point x plus h, so I have to look towards this forward, and you know which value lies at this forward is f of x plus 2h. So 1 over h square is as it is, and I am just applying forward difference on this point. So it will expand this term. So I will get f of x plus 2h. Why 2h? Because the forward value of this data is f of x plus 2h. Note that there is no operator now because we have applied the definition of the minus that value. So I'm not applying it x, I'm applying it x plus h. So the value is f of x h plus h. So del f of x plus h applied forward is equal to the forward value minus that value. Definition is still the same, but it applied at different points. Similarly, this minus sign will be there, and now I have to apply this definition which you already know. So the definition here would be f of x plus h minus f of x, bracket close, square bracket. So straight now you can clearly see this minus sign will be multiplying here, and these two terms, this minus and minus, will add up, no subtraction, and this negative multiplying with negative become positive. So I have to go to the next slide, and in next slide we will get the final answer. The final answer about second order derivative which we have to memorize or keep in our mind in a forward sense is second order forward difference approximately is defined as 1 over h square function's value situated at 2 units in a forward direction to h. You have to add h plus h, so you will move 2 units, minus 2 times of f of x minus h plus f of x. So why it is 2? Just to connect again, this minus f of x plus h, this minus f add up, and it will become plus h. Sorry, this is a mistake. This is plus h. Okay, this is a minus. Okay, so this will be your forward second order, or in a short form we can write it down like that as well. D f of x is equal to f x plus 2h minus 2 times of f of x plus h plus f of x divided by h square. Yeah, keep in mind for second order you have to divide with h. This is the forward difference. Second order, this is second order forward difference, forward differential operator. Operation. So if I ask you to have to compute numerically a second order derivative at that point, so what you do, you have to look for 3 values. For first order you only have to look 2 values, that is the value at which you want to compute and a value which is ahead of it. Now for second order derivative you need 3 values: value at which you want to compute the derivative, a value which is ahead of 1 unit of that value, and the value which is 2 units ahead of that value as well. So you need 3 points to approximate second order derivative. This is very important because you always found a relation that whenever you have a second order you need 3 points. If you have a first order you need 2 points. If you have 3 orders you need if you have a third order you need 4 points. So whatever be the order of the derivative you need 1 more point to express this derivative, and also the power increases as well here. So if I ask you, you have to compute, for example, third order derivative, let us d cube. How will you start? You said we have to do the same thing, we just need to apply, we have this relation, so what we have to do, we have to apply d on d square of f of x. So we have a relation of d square f of x. We just need to replace it, and then we have to shift d on each terms, and then use the first order relation define here accordingly at respective point, and then we will summarize it to obtain. So in this way you can define forward wise any derivative of the function. Similarly, I'm not doing it, but you can clearly think that you can do the same thing for the backward difference operator as well. Only thing you have to do is to define it backward sense, everything. That's the only difference. So if you apply backward difference sense, what will happen here? And forward we only use forward values of x, these values f of x plus h, f of x plus. But if you go on a backward, you will get f of x minus h and f of x minus 2h. Although you get a similar pattern, but you can verify it yourself. So this is the question. Maybe you can solve it or try to yourself. So this is the second order representation, but in a forward sense. You can define in this way any nth order representation, if you like, any nth order. But usually based on our not experience, second order, third order approximation, or fourth maximum. If you are dealing with some buckling, Levy problems in a column bending equations in a differential equation, you need fourth or fifth maximum. You don't need to go more than that. But if you want to do, you know the secret how you can do that. It's just you have to develop. So in books you usually find these type of differences. I hope I have clear to you that how we define the second order derivative based on the forward difference approximation. You can try this thing with higher order, and as well as for backward you will obtain similar equation. The only difference is here you will get minus 2h because you have to go minus h and f of x. Equation will be the same. The only difference is the involvement of the point. You have to move forward direction, in the backward you have to move in a backward direction. The only difference is, but this is what you have to prove yourself. Okay, for backward and for higher order of forward derivatives, if you like. Maybe I will ask these type of questions in a quiz as well. So you have to be work. It is not that difficult, hardly 1 page, 2 page working, but you can do it. But I gave you the concept now, you know the concept, so you can apply it to any type of differentiation. Here, whatever I explained to you is purely for the forward difference, keep in mind. Okay, but I want to do one little bit work, and then we will try to handle some examples as well if we have a time today. Is based on the second order representation of derivative based on central difference, which we have learned today. Central difference, if you remember, we just define it like that. So today we want to learn how the second order derivative based on central difference will be defined. So here we want to answer how second order derivative based on central difference is defined. Central difference is defined. Difference. Central difference is defined. So if someone like to take a break, he or she can do, because around 30 minutes or something left for this lecture, so you can have a break as well. Okay, so today we learn the basic definition of the central derivative. Central derivative says if you want to apply a central derivative, so what you have to do, you have this relation, a symbol of central, which is sigma f of x. Sometime I call it delta, ignore it. It is sigma, small sigma. because sigma is also this symbol. This is a large sigma or this is small one. So something like that. So sigma f of x is defined as, I have to define it on a basic definition of full length of h, but you always remember you can define it for half of the length or quarter of the length as well, because you have to make sure that the value you want to compute that difference must be at the center of the data set. But that's the main crunch behind it. It does not matter it is a half of the length or a full of the length. So I'm always defining in a basic definition of one length of h. So what we have for one length of h, f of x plus h minus f of x minus h. This is the definition of the uh, central difference operator. So you have to apply it like that. And similarly, if you want to apply a higher order, means that you have to apply central difference over the central difference again and again. So we can do that. But now question is, how can we define a derivative based on central difference? So first we have to think how we define a first order derivative based on central difference. Also the symbol of derivative first order. First, before going to a second order, we have to think about first order first, because we don't develop any relation. If I remember it correctly, I didn't tell that relation. Yes. So we have a relation of central difference, but didn't know how we can connect it with first order. So let's think about the first order first. So very simple idea. Tell f of x is equal to this quantity f of x plus h minus f of x minus h divided by, what I do, I will divide it by h. Now you are wondering why I am dividing it by h. Question is how I can, dividing by 2h, divided by 2h. Question is why you have divided. And similarly, keep in mind that h tends to 0. If this is the condition is imposed, we will get a derivative represent. How? So let's see the definition first, diagram first. So this is the point x, which we want to center by the value x plus h and the value x minus h. So this value is centered. So, and let's say somewhere there is an origin, and the graph of this function is represented something like that. So the rough diagram, and y equal to f of x. Okay. So we want to compute the central difference there. So we just learned that we have to look for his forward value subtracted from the backward value. So in what we do in central approximation, so this is f of x minus h, and this is f of x plus h. Keep in mind that in central you do not need information at that point. This is one of the important point as well. You are approximating something to the central value, but you do not need information from the central point at this moment. Keep in mind for first order. Okay, so you compute the difference, so you know that what change has happened from its left to right transition at this point. So what you have to do now in this case, why I divided by 2h, that's why I draw this diagram. So it is quite simple. So you are subtracting this quantity from this quantity. So what you'll get? You get certain height. So this is the height of this point, and this is the height. So if you subtract, you will get this height. So this is the change in y. That's what we do in derivative. Across the point, this point. But taking information not from the forward only, not from the backward only, taking information from forward and backward at a time. So we are computing a change at this point, but taking information from the forward value as well and from the backward value as well. Why? Because of the central approximation. So if I subtract this quantity by this quantity, I will get this height. And if I want to approximate this height as a derivative, what I have to do, I have to divide it by the separation between these 2 points. Similarly, rise over run. You remember in a calculus, tangent or slope. So I need to find the derivative at this point. So what I do, I use this idea, a central, and divide it by the length. So if we look for a length of this, we know that from there to there data has a length h, and here to here is also h. But we are computing a difference from this point to this point. So the total length is here h plus h, that is 2h. This is h, and this is also h. So total length is 2h. Or if you subtract x plus h from this x minus h, you will get 2h as well. So you can do it. So that's why I divided by 2h. It is not just a random thing. I divide it deliberately because of it. So what will I do if I assume that these points are very close to each other? That is, h tends to again 0. So these points are very close to this point. So I can use this to represent the derivative at this point as well, or not. Yes, we can do that. So in this case, we define it like that. If we impose a condition as well, limit of h tends to 0 in this case as well. So here we are also computing a sense of derivative based on the central approximation or central differences. So this will give me a relation, and what would be the relation is, this is basically a differential. It is sense of, I will not call it first order. It is a first order, but it is a derivative at that point. You still a differential at that point. So what kind of relation we will get? We get a first order approximation using a central difference. First order derivative is represented as central difference evaluated as f of x divided by 2h. So have you got the idea? Again, I told you there is no need to memorize things. You have to understand this point is central at a distance of the points which are at a h units. So I have 2h. What if I have a point that are half of the distance? So we know that if the points are half of the distance between them is h. So someone can use h as well here. So do not worry, you have to look for your data set and try to understand whether the data set are at a situation at a distance of h units or half of the h units. It depends on you how the data is defined and where you want to compute the derivatives. So I hope you understand. So this is the relation that we have for a central difference, a first order difference. Similarly, if you want to compute the second order difference, so what I have to do, I have to apply the second order difference over this quantity. It is approximate. So let's do the same thing for the second order approximations as well. This is the main question that we have to answer here, but we don't know the first order. So first we cover the first order relation. Now we are moving towards the second order representation. Keep in mind this relation. It is just like the forward relation. So we have this relation, first order derivative at a point approximately, because here in this case we are dealing with the central. It has to be very close to h. It is, so what we have, a central value evaluated at central difference evaluated at this divided by 2h. Again repeating, this 2 could be a h as well. It depends on the value that how you want to define the quantity. So here I am defining a data based on this following strategy, that if this is the x value, then the value situated to its x plus h, that is a distance of h units. And similarly, if this is the value, it is situated x plus 2h, a unit of h again. Similarly, we are not in fact we need information from backward as well. And similarly, this is the value x minus 2h, this is x minus h, this is also at a distance of h. All of them are at a distance of h, and this will continue if you like. And we are focusing here, and there must be some graph which are not interested at the moment. So based on that, so if I want to compute second order, what I have to do, I just give you a main theme. You have to apply operator over the operators. You have just learned this idea. What you have to do, you have to apply operator over the operator. So if you apply the operator over the operator, in this case what you will get, d operator is here, And you know that df of x in a central case, keep in mind this is the central approximation. We usually use the word central approximation, or sometimes I call it in a central sense. So central approximation. So this quantity is equal to that amount. So what will I will do here? I will replace del f of x by 2h. Again, maybe h you can find in books, no problem. Okay, so this is the representation. Now you remember what I did? This becomes second order f of x central approximation, and this will become 2h can be taken out as a common because h is fixed and 2h is also fixed. And I'm doing just to save a time, I am applying operator twice. So you remember del f of x, let me show you again. Del f of x is equal to f of x plus h minus f of x. So I'm replacing the relation there and shifting d as well. So what I will get, d f of x plus h minus d f of x minus h. I did two steps together with the hope that now you can understand and do things fast. Okay, I need this space, so let's mark it down. Okay, so this is the representation. Now student, similarly, so if I ask you, you want to compute d based on central approximation, how will you do that? D is shifted, but you have to do it in a sense of central approximation. So when you have to do in a central approximation, what you do, you will bring this you have to apply the basic definition there. So basic definition says if you want to compute something on the central differences derivative first order but based on the central approximation, so it is the same thing. If you're applying on x, you will get the following expression. So if you apply on x plus h, you have to deal with it accordingly. So let's replace it. We can say that df of x is defined by the following relation. So according to this criteria, 1 over 2h will remain 2h, and this will become del central del operated at x plus h. The only thing matter is at what point you are applying. So now I am applying at x plus h, not at x. So this is the only difference. It is x plus h, so I am applying at x plus h, del x plus h, and still we have to divide it by 2h. Minus, similarly, if I ask you what we have to do, you will say del applied to x minus h and divided by 2h. So these are the steps. Okay, so again what I can do here, I can take out 2 common as well as in fact 2h common. So I will write down here d square f of x, or I think it's better to go to the next slide. Maybe let's see. This becomes 2 into 2 4h square. Again repeating strength. Here I got 4 because I am applying a central scheme based on the full length of it. If someone is applying at a half of the length, maybe it get different numbers. So but that's not a concern. It is just a detail. So what we left inside is the central operator applied to a function when is evaluated at a point x plus h, minus central operator applied to a function when it's read at x minus h, bracket close. So what would be the answer then? 1 over 4h square del. Okay, so what if I apply a central difference at this value? So you know that it is the center of these two values, so you need to compute the difference of this quantity. But I am not applying a center at f of x, I am applying at this node. So if I apply a central difference here, so I have to look at what are the nodes at which this node is the centered middle. So I can see here this node, it is x plus, this is x plus 2h, x plus 2h, and x is a node that is middle this value. So what I can do, I can apply the simple definition here. So what it become now, f, I'm trying to write it small, f x plus 2h minus f of x. Simple. Okay. Now this negative sign, I'm writing this term bottom downward. So this negative sign is there and the bracket. Now I want to apply the central difference on this quantity. So I have to look x minus h is this term here, and this node is centered by these two nodes. So forward node is x plus h. So I have to compute f of x minus f of x minus 2h, bracket close. So if you try to take out common, you will get 1 over 4h square equal to f of x plus 2h minus 2 times of f of x and this minus will be multiplied to this minus, that will become plus f of x minus 2h. And I hope that I do not need to explain why I get minus 2 here. Just have minus f of x and minus f of x. Okay, so this is the whole term I get, and this is equal to the second order derivative of the function defined in the central sense. So let me write down this again on the next slide, and I'm shifting 4h square beneath this term. So I will get the following answer. D square f of x approximately equal to f of x plus 2h minus 2 times of f of x plus f of x minus 2h, and this whole quantity is going to divided by 4 times of h square. Sorry, let me verify. Yes, I have copied correctly. So this is the differential of this term. Second order derivative based on what? Based on central differences. Second order based on central difference. Okay, so let's think. If I said I want to compute second order derivative based at point x of a function f of x, so what discrete data I need? I need the value of the function at that point. Obviously we need that, and I need a data which is situated 2 values ahead of that data and 2 values backside of that data backward, and then I can compute the second order derivative based on what? On the central differences. This is the point that we have learned so far. So I hope you understand how to compute. And similarly, if I ask you based on central difference compute third order derivative, how do you do that? So you said we have to apply first order on the second order derivative evaluated based on central, and then this equation 1 over 4h square will be taken out common and d will be shifted to each of the value, but you want to use it central, so you have to apply the central definition on each of the function relation. So if you know the first order derivative, you can compute derivative for any order based on repeating the process again and again and checking which node it lies as a centered value. So this is the simple strategy. I hope all these concepts is clear to you, that how to compute derivatives and other things. I'm not going to add further. We will just look for a slight example which I think will not be able to complete in the time, but this is, I'm not starting the difference equation topic. We will keep it for the next lecture because that idea is based on these concepts as well, but let's do it separately. I just came up with an example that we can use to know how do exactly we deal with these things, the numbers, because so far it's all the just derivations and everything. So I'm making it as an optional to try this option as well. How do you compute third order or any other order based on central scheme, repeating the same process where the values are situated at a distance of h units from each other. Similarly, if you have half of the units, you can figure out accordingly. So almost 8 minutes left, so I'm just thinking whether we should start the example or not. Let me check. I have covered all the points, so nothing left there. We started from this topic. Okay, we have a relation, we have defined higher order forward. I gave you option to you can work with the backward as well for higher order. It is not that difficult, and these are the relations that you have to use. Okay, one thing, student, this is a continuous. If this is a continuous representation, then this is a discrete representation because you only have information discrete points. What does this means here? So for example, if I manage to complete it within time, it's okay. Then we will continue in the next lecture, and after that we will start find a difference equation topic. Also, these all the topics are linked with each other. We have to come back to this topic at a later stage as well. Okay. So for example, student, there is a metallic rod. Again, I'd like to give this example, and there is some heating coil, let's say thermostat type something, and you apply a current to that coil, which is transferring the heat to this metallic rod, and then heat is dispersing towards this direction. Higher gradient region, higher gradient means higher temperature region towards the lower temperature region. For example, just an idea. Let's say you want to know the temperature at this node. So what you did, you put a thermometer device that you can use. So you put thermometer there, and you want to know the temperature. So it is giving you the temperature on a device. Okay, so you know that you are noting the numbers from it. It's connected there, but obviously you cannot compute infinite amount of data. So what you did, you did like that. Okay, so you said, okay, I will make one table. Maybe I will just explain this example in this lecture, and then we will continue how to solve it and what are the relevant questions in it. So for example, I made it like this. I'm here. So what I did, I constructed and noted a table in Excel sheet or somewhere with time representing T and temperature, let's say, is in centigrade, for example. So you noted some data. How you? I will explain to you. Let's say this. So what you did, you set time 0, refer in seconds, refer to a room temperature. So you didn't start the experiment. You just switch on this device instantly. So at that time, we assume that this metallic rod at a room temperature. So let's say on that given day, the temperature you are indicating is something 37 degrees centigrade. So what you decided, that it is because once the process you now you started the heating, and this metallic rod starting to get heat, and the temperature will be rising at this point. So you are noting the temperature from the device continuously. So it is very difficult to note down the continuous data because it's changing in a milliseconds and microseconds. So what you did, you decided I will note down the temperature after every 30 seconds. Or let's say after every 10 seconds. So what you did, at 0 you have a room temperature, and at 10 seconds then you said I will note down at 20 seconds, or maybe your device or computer automatically note down for you and give you an Excel sheet: 30, 40, 50, 60, 70, 80 and 90, or maybe 100 seconds or whatever. 60 second means 1 minute and so on, we can convert, but we are noting only data in seconds. So 37, let's say after 10 seconds you note down something around say 37.1, let's say 37.5, and suddenly 38. It is just a random, uh, but we know that temperature will increase, that's for sure. Okay, if the heat is continuously supplying to that part. And similarly 39, let's say 40, 41, 42, 44, 45. Just a rough idea, it is not a so you note down this temperature, or an electronic device can give you an Excel sheet, whatever with experiment. Now what you want to know, so this is the heat that based on the coil you have generated in this coil. So this is how you computed the data. It could be an Excel sheet where you have a column time and data, or it is the temperature. So what you want to do, I will solve this problem in a later lecture, but let's say you want to analyze what kind of metallic deformation happen in a metallic rod based on the temperature variation. So you want to know that you put some load here, and you want to have a heat there, and you want to see how the deformations happen. For that you need to understand the temperature variation first. So what you are doing this, you just note down the temperature, and you want to see how the temperature changes within this metallic rod based on this data, numerical data. So whenever we say changes, it means we want to discuss the change in temperature with respect to the time. This is what we want to discuss at any point. So question is how we will do that, and how will we compute it, and any other thing that will I will connect in the next example. So far I like to end here, and this is the lecture number 3, which we will discuss in a live session after the next live session, not in the next one. In the next one, that is on 17th of June, we will discuss something related to the lecture number 2, which I have uploaded already. So student, I would like to thank you for all of you on the second lecture and for your time and the patience, and you are all requested to note down the questions that you have, and I gave some examples that you have to complete as well. So try to do these as well. It's not compulsory, but try it yourself. I would like to thank you for your time.